Organic nomenclature. Naming organic compounds is completely different from naming inorganic compounds. And organic chemistry has its own system of nomenclature. This is necessary for a couple of reasons, but the overall motivation, to be able to identify and write the formula of a compound from its name, is still the same. First, while there is a lot of variety in inorganic compounds, most of the compounds are pretty small, at least in the sense that there are not very many atoms involved. The variety comes from the fact that different elements are involved in the different compounds. With organic compounds, the same elements are involved in most of the compounds, specifically carbon, hydrogen, oxygen, nitrogen, and a very few others. The variety comes from the different arrangements of these elements. So we need a way to distinguish these different arrangements. This requires a different system. Second, it is rare, though not impossible, for different inorganic compounds to have the same formula. This is a very common thing for organic compounds, so we need a system that can distinguish these differences. The system we use breaks the name into 3 parts, each of which gives specific information about the compound. The central part of the name is the base, which gives us information about the number of carbons in the compound. This is based on this list. This is only a partial list because organic compounds can have many more than 10 carbon atoms, but for the most part you will not need to worry about any others. One other point is that organic compounds are thought of as hydrocarbons, that is, compounds of carbon and hydrogen, with other things attached to them, and the base is determined by the hydrocarbon foundation of the compound. However, this means that the base does not always directly indicate the number of carbon atoms, particularly since aromatic compounds have different basic components. The second part of the name is the suffix, which indicates the type of family the hydrocarbon is part of. There are 4 basic types: alkanes, alkenes, alkynes, and aromatics. The first 3 are very similar in the way things are named, with significant differences for the aromatics. Alkanes are compounds with no multiple bonding in the basic carbon chain. The suffix for alkanes is ane. These are also called saturated hydrocarbons, which means that they have as many single bonds and as much hydrogen as possible. Ring structures have the carbons forming a ring instead of a chain, and take a prefix of cyclo to indicate this. If there are no double bonds, they still have the ane ending. Alkenes have 1 or more double bonds in the basic carbon chain. Alkenes and alkynes are called unsaturated because they have less than the maximum amount of hydrogen. We indicate the position of the double bond with a number that tells which carbon in the chain the double bond starts from. We number from the end that produces the lowest number. Because the double bond is stiff and cannot be rotated without breaking the bond, there are 2 ways the chain can be aligned. These are called cis and trans, depending on whether the carbons are on the same side or opposite side of the double bond. Alkynes have one or more triple bonds, usually only one, and end in YNE. They're also unsaturated. The position of the triple bond is given in the same way as for alkenes. For aromatic hydrocarbons, it is important to know what the basic molecule is. The molecules are planar and tend to have one or more six-membered rings attached to each other. The most common aromatic hydrocarbon is benzene, which has one six-membered ring. These rings are very stable and are found in all aromatic compounds. The stability is derived from a delocalized pi system produced from the p orbitals on each atom. Here are several examples of aromatic compounds. Benzene has one six-membered ring. Naphthalene has two. Anthracene has three. Toluene, or methylbenzene, has a substituent on the benzene ring. When two substituents are added to the benzene ring, as in the examples here, we can have orthodinitrobenzene, also called 1,2-dinitrobenzene, metadinitrobenzene, also called 1,3-dinitrobenzene, or para-dinitrobenzene, also called 1,4-dinitrobenzene. These are three forms with the same formula. The final piece of our nomenclature is the prefix, which tells us what substituents, groups attached to the longest chain, are present in the molecule and where they are. To name a compound, identify the longest chain in the molecule. If the molecule is cyclic, like cyclohexane, or aromatic, then identify the ring structure and use that as the base name. Number the chain from the end nearest the first substituent encountered. If there's more than one longest chain, choose the one that gives the lowest number for the first substituent. As prefixes, list the substituents in alphabetical order, along with the number of the carbon to which it is attached. If there is more than one of that particular substituent, list all the numbers. For substituents that are other hydrocarbons, the ANE ending is replaced by YL. Double and triple bonds are included in the longest chain if possible. Occasionally, certain substituents are listed as endings, depending on the importance of the particular group. For example, we could name CH3, CH2, CH2, OH as either 1-hydroxypropane, if we use the OH as a prefix, or 1-propanol, if we use the suffix. The most important and most common substituents are shown on the next slides. The specific structure is what the name is associated with, and so it is important that you note the particular structure. Note that most of these involve oxygen. An alcohol has an oxygen attached to the carbon atom and to a hydrogen atom. An ether has an oxygen attached to 2 carbon atoms. Both aldehydes and ketones have a carbon-oxygen double bond. The difference is that the carbon that makes the double bond to oxygen is attached to a hydrogen atom in an aldehyde, but to 2 carbon atoms in a ketone. One way of thinking about it is that an aldehyde is at the end of a carbon chain, while a ketone is in the middle of the chain somewhere. Carboxylic acids are like a combination of the aldehyde and the alcohol on the same carbon atom. We have a carbon atom doubly bonded to one oxygen atom and singly bonded to another oxygen atom. This particular arrangement allows the hydrogen to be easily pulled off, which is what makes the structure acidic. An ester has a singly bonded oxygen connected to another carbon atom, rather than to a hydrogen atom. This slide shows 2 functional groups that involve nitrogen. Amines are like alcohols, except that the other atom is nitrogen instead of oxygen. One of the results of substituting nitrogen is that there is another bond on the nitrogen. Amines may be attached to 1, 2, or 3 carbon atoms. The amine group is basic and is the source of most of the basic organic compounds. Amides are like esters, with a nitrogen substituted for the singly bonded oxygen atom. Let's try to name this molecule. The longest chain, a heptane, is highlighted and numbered from the end closest to the first substituent. There is 1 ethyl group and 3 methyl groups. So the name is 3-ethyl 2,4,5 trimethyl heptane. Why would this, highlighted in blue, heptane, not be the best 7-carbon chain to use for our compound? Because whichever end we start from, the first substituent is on the 3rd carbon, while we get one on the 2nd carbon with the other chain. Let's try this compound. We again have the longest carbon chain highlighted as a heptane. We have a methyl group on carbon 2, an ethyl group on carbon 3, an amine group on carbon 4, and a hydroxy group on carbon 5. So the best name, the one with the substituents in alphabetical order, is 4-amino, 3-ethyl, 5-hydroxy, 2-methyl heptane. It could also be named 4-amino, 3-ethyl, 2-methyl heptane 5-ol if we choose to use the hydroxy as a suffix.